So again, we're going to look at both. We're going to look at the magnetic field created by a free charge moving in space. We are not going to spend any time on that except to get the idea for what it looks like. Now, it's the problem with and you'll see in just a moment, it's just too dynamic. We will spend a lot of time talking about the magnetic field created by a current carrying wire. But do you remember that when we dealt with Gauss's law, we really only had a couple of shapes that we used? Like we used Gauss's law to talk about the electric field around a point charge. We used Gauss's law to talk about the electric field around a sphere of charge. We used Gauss's law to talk about the infinite line of charge. And we used Gauss's law to talk about the infinite sheet of charge. And although there were other applications to Gauss's law, that was really our limiting factor. We're going to use Biot Savart, and in a similar way, we'll have limiting factors for what we can use, and we'll have Ampere's law, which will have its own limiting factors. For Coulomb's law, we had similar, like the ring of charge, we had a bar of charge, we had a line of charge, but we really didn't use it outside of those circumstances. Maybe an arc of charge, if you'll recall. Those are kind of our limiting factors for how we dealt with Coulomb's law if it wasn't just point charges. Ampere's law is going to exploit symmetry the same way Gauss's law did. Biot Savart, not so much. So here we go. Let's without further ado, let's go ahead and take a look. And let me dim the lights a little bit. I'm ordering a new bulb, but the district would tell me you don't get to buy new bulbs. I want to talk first about what this looks like and how we use the right-hand rule, and then I will dive into the math. I think you'll like that better. So let's start by just identifying some variables. Let's talk about a point charge as it moves through space. So here's my point charge. Now, if I have a point charge sitting in space, it does create an electric field. We know that. We know what the electric field looks like. We know the point charge has spherical symmetry in space. That will still be true even though we're going to focus on the magnetic field. So even though this point charge creates an electric field, and that electric field will be the same electric field we talked about before, we're going to ignore the presence of the electric field so that we can focus on the creation of the magnetic field. Is that okay? So keep that in mind. That means we need to give the particle a kick. So let's just say the particle has been given a velocity in this direction, and that the particle is traveling at a constant velocity and is traveling in the same direction the whole time. A point charge traveling through space generates a magnetic field around itself. The magnetic field is circular. It doesn't have a point of origin or a point of termination. Magnetic fields don't have origins or terminations. They're circular. They're not like electric fields, where electric fields originate at positive charges and terminate in negative charges. Magnetic fields have no point of origin. I'm saying that over and over again because you're going to have to get used to this idea that the magnetic field is significantly different than the electric field. To help us picture this, I want to draw kind of a line that's in the direction of the velocity both before and behind our charged particle. So this blue line represents the straight line path of our charged particle. As a particle moves, it creates a magnetic field around itself, and that magnetic field fades away the further away you are from the charge, the same way the electric field does, meaning it follows an inverse square law, and therefore the further are you away, the more the magnetic field attenuates. But the magnetic field is generated ahead of the charged particle and gets bigger as you get closer to the charged particle. And then it begins to get smaller again as you're on the backside of its motion. That's what the magnetic field looks like. It gets bigger and bigger as you are closer and closer to the charge. So if you are, say, here, in this location in space, point P, you may not detect any magnetic field, but as the particle gets closer and closer to you, you will feel the magnetic field increase as it gets closer to you and then decrease again as it passes you. The magnetic field, however, is circular and travels in circles around the charged particle. And although you may not fully be able to appreciate the direction of that magnetic field, I'm going to use some other symbology that you do know to explain that the way this particle is traveling, on this side of the path, the magnetic field would be into the board, and on this side of the path, the magnetic field would be out of the board. We'll use the right-hand rule to determine direction of the path. Direction of the magnetic field. So there's two ways for us to determine it. I'm going to show you one way to determine the direction of the magnetic field right now. So we're going to use the curl rule because it's really easy. We'll use the three-finger rule in a minute, and it's a little bit harder. But let's use the curl rule right now first to figure out the direction of the magnetic field. It's real simple. You point your thumb in the direction of the motion of the particle, and your fingers curl in the direction of the magnetic field. So if I point my thumb in the direction of V, my fingers are curling in the direction of the magnetic field. So that's why it's going into the board here, penetrating, coming out of the board, and going around in that circle. Does that make sense? So if you were located right here, the magnetic field would be downwards because the magnetic field is traveling in a circle around the path that the particle is traveling on. The way Biot Savart works is twofold. This is the version of Biot Savart that's for a point charge traveling through space, and it looks like this. It is will require a summation. So we're talking about the partial magnetic field that you've experienced from the charged particle. Of course, you'll have to add up all of the possible components of this if there are multiple moving charged particles. But it looks like this, the magnetic field from a single point charge. So I put dB here, but this would be if you were adding it up for multiple charged particles, you'd have to add them up. Is that okay? So I want to leave it like that because if you had a whole fleet of charges, you would add them up. And it looks like this. It is, first there is a constant of proportionality, mu naught over 4 pi. That's out front. It's a constant of proportionality. Mu naught is the permeability constant. And I think this is the first time you are seeing it, so we'll talk a little bit about it in the future, but it is a constant much like the permittivity constant. So this is called the permeability constant. So it serves the same role as permittivity. It's how easily a magnetic field can be set up in this region of space that you're in. So with the naught there, we're talking about the permeability of free space. So it takes the same role as epsilon did for electric fields. So this is the version of epsilon, but for magnetic fields. And it's called permeability. So we have the permittivity constant and the permeability constant. Now this part I think is going to be not obvious, but you'll understand the components. There's the size of the charge, the velocity, and then this part, just give me a minute to write it out. It's cross r hat divided by r squared. So q v cross r hat divided by r squared. We've talked about r hat a little bit in the past, but it's making another appearance here today. I think the last time we talked about it was when we talked about Coulomb's law. But here it is again. This is going to be more a part of this conversation. The r hat is a unit vector that points from the point charge to the location in space where we're looking for the magnetic field. Okay, that's what r hat stands for. It is a unit vector, so its size is 1. But it contains directional information. So r hat is in the direction from where our point charge is to where we're observing it in space. So just to make that clear, this red line, or this gray line, depending on how you see it, represents R. Because R is the actual length from where the point charge is to where we are in space. That's in the denominator. R hat carries the direction information. It carries the directional information. This cross here is the cross product between the velocity and R. So if you wanted to figure out the direction of the magnetic field, you would use the cross product here to do so, the three-finger rule. So we'll come back to that in just a minute if you don't mind, but these are the pieces of how you would calculate the size of the magnetic field. Now, if there was more than one charge moving, or if you had an object that all had charge, like a bar of charge that was moving through space, you would have to do the derivative. You have to do the integral. You would add this up over all of the point charges. And if it was an object that was, say, had so what do I want to use here? If it was a bar of charge, then this would change to dq. And you would integrate over each piece of charge in the bar as it moved through space. So that's how Biot Savart works. The problem is that it's even more complicated than I'm describing. Because right now we just have a single point charge passing through space. And we could only figure out the magnetic field instantaneously at this moment. Because you understand the charge is moving through space. So in a few moments, it's going to be over here. Thus, the direction of R changes, V stays the same, but R changes as well. So we're going to see a change in the magnetic field as this point charge passes us. So using Biot Savart to figure out the magnetic field is very transient in nature because it only exists for that instant when the particle is located right there. And then it's going to move the instant later, thus changing the size of the magnetic field. So for all intents and purposes, we will not use any point charge calculations. It just doesn't come up very often in any of the work. It's never on the exam. It's not actually part of our curriculum directly. Meaning this is Biot Savart, and I'm supposed to teach you what Biot Savart is like, but we're really only going to deal with Biot Savart in applications when we talk about a current in a region of space. Because that's something that, at least once you establish a current, even though we may have to integrate because we have to integrate over the whole line or over the whole loop or whatever our current is, at least there we have the possibility of real integration. Here, what's the point of doing this integration if this is only instantaneous in nature and the next instant it's gone? So this doesn't come up very much, but I think it's important that you understand, even if we ignore all of that, that a point charge traveling through space is generating a magnetic field. All right, so I just wanted to give you guys this impression. Like, what's happening around a point charge is complicated, but let's go to a more realistic issue. There are two examples, that I think you should be capable of doing at any time leading up to the AP exam. Biot Savart is really good at one of them and mediocre at the other. But Ampere's law is good at one of them and can't do the other. Is that okay? You follow that line of reasoning? So the truth is, Biot Savart could solve for the magnetic field for any current or set of charges. Just like Coulomb's law could do any collection of charges or charge distributions. Unfortunately, there are charge distributions that are so complicated that it's very hard to use some of these techniques. So the one we're going to do is the straight line of current. Remember we did the line of charge? This is going to be a line of current. Biot Savart is okay at doing this one. Ampere's law is one step. Biot Savart will be many steps. Do you guys remember the infinite line of charge and how Gauss's law was like 3 steps, but calculating it using Coulomb's law was painful in the extreme and led to an integral that, well, most of you have no idea how to do because you can't even integrate yet. And even you BCers probably looked at it and go, wow, that's fun. That's interesting. Knock yourselves out. Yeah. This will be similar. And Ampere's law will do it in a step, quite literally a step. On the other hand, we're going to do a loop of charge. A loop of charge can't be done by Ampere's law, can only be done by Biot Savart. However, both of the results are very similar in nature. In fact, the results of both a straight line of current and a current loop look almost the same. You need to memorize the results of both of these. You'll need to have memorized what the magnetic field is near an infinite line of current, and you'll need to memorize what the magnetic field is at the center of a current loop. You understand, you just made loops of wire. Magnetic fields and loops of wire, they go hand in hand, they're bros. So we'll be seeing it a lot. So let's say that this is a line of current. So we have a wire in space that has a current in this direction. I do need to remind you that current isn't a vector. So when we talk about the vector portions of this, the vector part will be the fact that the actual wire creates the vector. So whatever the wire's direction is, that's the vector at that moment. We're going to identify a region in space and call it point P. And we're going to try and find the magnetic field at point P. Now, Biot Savart for a current-carrying wire has a much different look. Again, we're going to talk about the fact that we're going to have a portion of the magnetic field because we're going to have to add up all the contributions for the entire length of the wire. So when we talk about an infinite wire, we're looking at adding up the contributions to the magnetic field from something very far away all the way to the other direction very far away. And we're still going to have our set of constants in the front, mu naught over 4 pi. And then here's what Biot Savart looks like for a current-carrying wire. We multiply by the current, and then we have to choose a piece of the wire. ds represents a piece of the wire someplace in the region of space where the wire exists. Cross r hat. Again, r hat is a vector that points from the wire to our place in space. And in addition to that, we're going to have in the denominator how far away from the wire we are, r squared. Okay? So, I think you probably know some of the pieces of what we're going to have to do. Just like when we did Coulomb's law and we identified a piece of charge, for this, we're going to use a piece of length. Some piece of length on the wire. ds is a piece of the wire, so it represents a piece of length of wire. So we'll choose someplace, say here, and call this ds. Now, one of the great things about this is remember how we had to come up with like charge density and all that? We actually don't have to do any of that. The current in the wire is the current everywhere. And we're only going to deal with wires that have the same cross-sectional area everywhere, but it doesn't matter. The current is the same everywhere in the wire. So we won't have any of this charge density or anything like that, or some weird current density, not for this. It's just whatever the current is what the current is. In fact, it is a constant. In all of these integrations, it will come out front, because the magnetic field generated by this current is not going to depend on where you are on the wire. Now listen closely, and I want this in your notes right now, because it's going to come up later. In this wire, the current is the same everywhere in the wire. So I'm saying that the current is not dependent on where you are in the wire. It's not location dependent. In the future, we will have currents that are time dependent. So if you have a current in this equation that is time dependent, you still treat it like a constant, because it doesn't depend on location, and this integration is about location, not about time. This doesn't seem like much now, but the entire last unit is about changes in current. The entire unit, the entire month and a half. You generate things using changes in current and changes in magnetic field. But for this, and for everything that we do when it comes to integrating current with respect to location, the current is a constant. So even if it changes with respect to time, it does not change with respect to location, and this is a location-dependent integral. All right, that being said, we need to establish a couple things, and I think this part's going to be the same kind of stuff as we talked before. I'm going to draw a line that represents R. This R represents the distance from our piece of wire to where we're located in space. But I'm also going to introduce another variable, and I think you're probably aware of this variable before we even get started. We are a perpendicular distance away from the wire at that location P, and so I'm going to call this Z, just so we have a different variable. This is a variable that represents how far we are away from the wire. I would use R here too, but then we'd get confused. So I'm going to say Z just as a placeholder. Is that okay with you guys? All right. Because we need one, and I think you can probably see why. R is going to change all the time, but Z is a constant. We are always going to be this far away from the wire. You follow me on this? So when we're adding up all the contributions to the magnetic field, R will always be different, but I think if we can express stuff in terms of Z, we'll be happier. So let's go ahead and go one more variable. I'm going to say that this distance is X. The reason we use ds is a placeholder for the length of the wire. So if we had a curved wire, it would be an arc length. We have a piece of straight wire. And because it's a piece of straight wire, for this example, ds is a little bit more in the direction of x. So although this ds means any length of wire, we are establishing our coordinate system. So I'm going to say that dx represents a little more in the x direction, so that I can use x and z for replacing r. Does that make sense? Just like we did before when we did problems like this, we want to try and create something that we can integrate over. And we want to integrate over the whole wire. Let's try and work some constants into this. And one of the constants we can work in is z. Because I think our answer is going to have to do with z, how far away from the wire we are. Now, without starting the math part, let's handle that cross product. You guys are aware that cross products have a magnitude, and the magnitude of a cross product introduces the sine function, where the sine is an angle between the first vector and the second vector. You guys follow that okay? And that vector's here. We have ds, which is the direction of the wire, and dr, which is the direction of r. So if I was to superimpose that here, ds is this way. This is the direction of ds, and dr is this way, and this is the direction of dr. Not dr, just r hat. Sorry, r hat. So those are our two directions. The cross product, the magnitude of it, will introduce sine, and it'll be the sine of the angle between these two. So we can either use this angle or this angle, but if you know anything about sine, you know that it doesn't matter which of these two angles we choose, it will be the same, right? Because the sine is the same in the first and second quadrant, this produces the same sine. You guys all okay with that knowledge? But this is where the angle is measured, not over here. So I could rewrite this for magnitude and say dB equals mu naught over 4 pi I ds sine phi over r squared. And I can remove the vector bar over dB. So now I'm just talking about the magnitude. But I should use the right-hand rule to figure out the direction of the magnetic field at point P. Now I already gave you since we are splitting this up into 2 different days, and we're not in the throes of what we talked about yesterday, just a brief, real quick reminder. The idea here is our rule has something about this piece of wire. So the point of the ds here is to indicate that there's lots of contributions to the magnetic field from the moving charges located everywhere along this wire. So this ds represents where are we on the wire at the instant we are trying to figure out that piece of the magnetic field. So we need to know how far away from the wire we are, but we also need information about the relationship between the direction of that wire and the direction to where the point is in space. So that's what that ds cross r is. That produces a sign in our function, and that sign is based on an angle between 2 vectors. Those 2 vectors are ds and r. So the r hat here adds no, it doesn't add any size to the problem, right? It's just you're multiplying by a value of 1, but we're using the r hat to represent something that has to do with the angle. So that, if you want to think of all of this as nothing more than adding the sign of the angle into our function. That's really all it is. So you don't have to worry about well, why is there an r here? How much does the r adds nothing, not even units really at this point. This is our constant, and we're going to see that pop up a couple of times. The funny thing is we had to figure out a way of expressing all this. So I put some placeholders in here yesterday, and so we are looking at this point right here being the point directly across from where P is in space, so where Z represents that perpendicular distance to the wire, and X is a distance along the wire to our piece of wire that we're studying. R is the actual physical distance between the piece of wire and our point in space, and phi is the angle between ds, our piece of wire, and r hat. And ds is a placeholder value meant to imply that would be for any arc length related to the wire, so if the wire was bent or curved. We are replacing that with dx since we're using a pointer of x. Does that cap off all the reasons why those things are there? All right, so I would probably state that if I was writing this yesterday, I was probably getting in a hurry because the bell is getting close to ringing, but we should replace that ds with dx here as our integrating variable. Now, it's at this moment that we would do something similar to what we did first semester, which is we need to decide how we'd like to present this. I'm suggesting that we integrate along x, but that means taking every variable that's related to x and replacing it with a version that has x in it. We could use a different integrating variable. For example, we could probably represent this in terms of d phi if we wanted, and redo all of this in terms of d phi. But I find that it's generally easier to integrate along a length for stuff like this if we can. At least it will make a lot more sense for us if we integrate along a length. So I think we should leave everything in terms of x for this. But if we wanted to, we could find some way of expressing ds in terms of something like maybe r and phi if we wanted. But again, I think we should stick with the way it is and stick with dx. You guys okay with all that? So if you are a calculus student, I don't mean like you're in the calculus class and you're doing homework. I mean if you're a student of calculus and you would like to learn more, we could talk about what it would take to redo this problem in terms of phi. Now that you guys have a little more calculus underneath you, there are some things you would have to do if you wanted to express this in terms of phi. Some of them are good, some of them are complicated. I mean, we're going to have a relationship here in a minute that has phi and x in the relationship. I mean, just looking at that, I think you guys realize that sine of phi is z over r, correct? So, and we can replace r with the square root of x squared plus z squared. So if we want, we could write sine of phi in terms of x. So this is a way to do it. I'm not sure it's going to be a useful thing to do, but we could do it this way. We could rearrange this, solve this for x, and then put that in our function for phi by taking the derivative of both sides. I don't think that's an easy way to do it. So I think we'll stick with replacing phi with x, if that's okay with you guys. So that's how we'll do it. I think that's enough information here to do some substitutions over on the right and start replacing variables. So dB is going to be equal to our constant mu naught over 4 pi times I dx. And then in the denominator, we're going to have x squared plus z squared to the 1/2 power quantity squared times the sign, which is going to give us z over square root of x squared plus z squared. There we go. We have everything in terms of x. Any questions about that? Alrighty. We don't need our picture anymore. We're here for math now. We can clean this up some. I'm going to take everything that's a constant and pull it out of the function. All okay so far? All right. If I want to find the magnetic field, I need to integrate both sides. Everything here is a constant, so I'm not particularly worried about that. But if I integrate both sides, and I'm so excited to hear that you guys finally got to draw the integral symbol in your calculus class. That's very exciting news. Do they draw it different nowadays? Is there a new modern way to do it? Or is it still old school big S like this? All right, cool. Hate to find out that I'm doing it the old way. I'm going to go ahead and put the integral symbol on the other side of the constants. And we have to set our limits here. Your limits are from negative infinity to positive infinity if it's an infinitely long wire. Or you could go from 0 to infinity and double your results. Either one of those is fine. You guys who are just getting into the integral symbol, probably best right now. That would not make it too crazy, but remember, it's just a summation. So if you know that you're doing a summation and you know that two sides are symmetrical, you could just split it in half and do only one side of the integration. It's almost always easier if you can work a 0 in. We're not going to do this integration. I really had no intention of it for a number of reasons. And the number one reason is anybody who has done any calculus realizes that this one is not going to be particularly easy to do. You can't U sub for this one. It's similar to the one for the electric field. There's no simple U sub. You will have to use a trig identity to actually get to this integral. But you guys who are in BC, that's a good exercise for you. You should perform it. You should go through that exercise because you guys in BC should be learning at this point because you're in BC. Right? You guys should be at the point where you've done integrals and you're learning all the different ways that you could possibly get around something like this where there's no simple U sub. This one also can't be integrated by parts. So you need a substitution for this. And there's a trig substitution that will provide it. But I want you to understand, on the AP exam, they're never going to paint you into a corner with an integral that is anything more than a straightforward one-step integral. They may make you do a U sub. We've done a few of those at this point, but nothing particularly complicated. Your integral is always going to fall into the power rule, a trig rule, or the natural log or exponential. It's going to be one of those. That is not this. And so I want to do our next geometry, and it's a geometry that Ampere's law can't solve, which is why we have to use Biot Savart. And this is probably, when it comes to magnetic fields, the most important example we're going to use. The infinite wire is used a lot, but not as often as the current loop. So let me draw it big enough where we can kind of get some diagramming done here. This is going to be drawn as a single loop of current, and we'll say that our loop of current has a current in this direction. Now, before I launch into all the theoretical stuff here, obviously it's impossible to have just a loop of current. What you could have is you could have a wire coming this direction, bend it in a loop, and then you're going to have a wire exiting this direction. right? That's a current loop. Or you could have a wire, this might be more reasonable, a wire coming this direction, break this way, go around in a circle, and then coming out this direction. Does that make sense? But what this also should suggest to you, like the current loop you made in class, right? That you could have lots of loops if you wished, right? And they would all add up to be one basic current loop with lots of current passing through it. So what you guys built with your motor was a single current loop. Although inside of it was multiple wires, the whole thing was to do an additive response, adding lots of current together to increase the current. Because it should be clear from the function that if you're trying to build a strong magnetic field, one of the ways to do so is by increasing the current. So it's front and center right there. With every multiple of loops that you make, you create multiple values or powers to your magnetic field. So if you double the loop, suddenly the magnetic field is twice as big. Now, you didn't know that you were doing this when you were making your current loops, or you may have because you've played with this before. But we talked about our motor as a force acting on a current-carrying wire. Right, that's how we talked about our motor. But you guys have played with magnets since you were kids. You know that magnets try to align with each other. Right? Many of you bringing the magnets back to me, you pop them together. They will forcibly try and flip each other so that they're all aligned. Their north pole matching up with the north pole of the other magnet. Well, that's really what your motor was doing. When there was current, it was creating a magnetic field inside the center of your loop. And because of that, it was trying to line itself up with the magnet that you placed on the table. So how does it do it? By applying a force to charge particles, clearly. But it's hard to know whether that force was actually acting on the wires or if this was the two fields interacting. Now, you guys know that magnets will line themselves up. You've seen it happen. But the actual force is a force on the charge carriers, even for permanent magnets. So there has to be an object that's experiencing a force. A field can't experience a force. Only an object can. The object has to have mass, has to have inertia. An object experiences a force. So that's what causes the motor to flip, even though what's really happening in our heads is that we're aligning the magnetic field. This is why some of your motors work better if you just moved the magnet around a little bit to put it in a more optimum place, because you didn't really know what the field looked like around the little disc magnet you were using. Now, before we go and do the math here, let's take a look at our right-hand rule to get an understanding of what the magnetic field must look like here. So using our right-hand rule, and I'm using the curl rule for this. If I point my thumb in the direction of the current, then I'm noticing that I'm going to have my fingers are always out of the board when I'm inside the loop and into the board when I'm outside of the loop. Meaning there is a magnetic field that goes around the wire here, and it is out of the board or out of your paper on this side of the wire and into the board on this side of the wire. And that loop is occurring everywhere around our loop. We have these little magnetic field rings all around our loop. Now, the magnetic field inside the loop isn't uniform. And we're not going to talk about places that aren't symmetrical. So when it comes to finding the magnetic field, the only place we're going to be interested in is finding the magnetic field at the very center of the loop. Okay? The magnetic field isn't necessarily the same value over here. There's ways to try and make the magnetic field more uniform inside the loop, but that's not happening today. We're just talking about a single loop of current. Everybody okay? Everybody understand what I'm saying? Now, we're going to talk about something called a solenoid the moment we come back to this. And a solenoid is a collection of loops that goes for a long distance. That's one way to start collimating your magnetic field and creating a more uniform magnetic field. But so far, none of the things we've looked at will have a uniform magnetic field, which is why, in the case of this question, we're only going to talk about the magnetic field at point P, which is the very center of the loop. All right? So, step one, we're going to establish what we're going to use for ds. And for me, our ds is going to be a small piece of arc located somewhere within our loop. This is going to represent our bit of length of wire. And for argument's sake, that suggests a vector for ds that is tangent to the wire and stretches in this direction. So this is going to be the direction of, not r hat, this is the direction of ds. R, on the other hand, points from ds to point P. So this is R, but it's also the direction of r hat. So for this example, R is actually the radius of our loop and will be the same value for all of our pieces of wire. So unlike our example before where R was different for every piece of wire, R is going to be the same for every piece of wire. And so I'm going to use capital R to represent the radius of our circle. Everything okay? Now, three-finger rule should agree with our curl rule. So our three-finger rule, if you'll remember, is to take your pointer finger, point in a direction of ds, and then roll your wrist until your middle finger is in the direction of r, and that tells me that my magnetic field will be out of the board at point P at the center, which is what we predicted with our curl rule anyways. Okay, so we do need to find a way to write ds, but before I do that, I'm going to throw out a postulate that I think that for every single piece of wire, the angle is going to be 90 degrees, right? The radius will be always perpendicular to the tangent. So when we do our sine in a minute, it's going to be the sine of 90 degrees. I'm bringing that up because I also want to add a new angle to consider. Although this angle represents phi, I think we can describe ds in terms of an angle if we wish. Right? We could write ds in terms of an arc length, where ds is equal to r d theta, where d theta is a small piece of small piece of angle. If I was to blow this up a little bit and consider that there's this side of the angle and this side of the angle, this right in here, that would be d theta. Does that make sense to everybody? Okay. So I'm going to establish that right here is 0 for the angle, and that we will integrate from 0 to 2 pi, taking us all the way around the circle. Does that make sense to everybody in the room? Because we're going to need a place to start if we're going to be using theta as our integrating variable. So my plan is to use theta as my integrating variable. All right, so I'm going to go ahead and start making some substitutions into my function. First, I'm going to collect my constants that I have so far, and I think I'm going to have some more in a minute, but I'm just going to collect the I. I'm going to replace ds with r d theta. I'm going to go ahead and replace the cross product with sine phi, but I know phi is 90 degrees. And I'm going to replace lowercase r with uppercase r, saying that I have taken the time to know what r means, and r is the radius of this circle. So there we understand all those substitutions, because One of the problems that we've come across in grading your tests is you're great at memorizing something that you've seen on the board, but when they change something, you have a harder time because you don't have the process. So each thing that I replaced was in service to trying to make sure everything was in the same terms, but each thing had a reason for its replacement. So this was to replace ds with something I felt we could integrate easier, something that showed a starting point and an ending point. So I replaced ds with rd theta, knowing I could integrate a circle from 0 to 2 pi. Next, I replaced lowercase r with the radius of the circle, instilling in us that the lowercase r is a placeholder indicating the piece of wire's distance from the point in question. So I replaced it with capital R representing the radius of the circle. And the cross product was evaluated, and we put the sign in place, the sign of phi, but phi is the angle between ds and r hat, which in this case is 90 degrees. Go ahead.
Can you just go over again how you figured out that ds was RD theta?
Well, yeah, I mean, arc length is the product of a radius and an angle measure, so I just use a really small piece of angle. Does that make sense?
Yeah.
Okay. Now, I'm over-talking everything. Sine of 90 is 1. One of the r's cancels. R is a constant. So I can collect all of this together now. And I am left with just d theta here in our integral. This is an integral I think we can handle. So I want to get the entire magnetic field at the center of the loop. So I'm going to integrate both sides. I have to set my integration parameters, but I don't have to do very much here. I'm going to integrate from 0 to 2 pi. That'll get me all around the circle. So the left side becomes B, our magnetic field. The right side, mu naught I over 4 pi r. That's just all the constants. And I'm going to integrate, well, there's nothing there. So if there's nothing there, there's an implied 1. But I'm not going to write it as 1. What am I going to write it as? Theta to the 0 power. All right, so I'm going to use the polynomial rule here. So I introduce theta to the 0 power because it's the implied 1. And now I'll use the polynomial rule. So the polynomial rule says add 1 to the exponent and then divide by my new exponent. And then I have to evaluate this from 0 to 2 pi. Now, I'm not trying to insult your intelligence if you know how to do this and you would have not needed that right through. I'm doing this for the folks who don't have this at the back of their hand and need to think about it a little bit more. But are we all good with it? Talked it through? All right, there's not much more to do here except substitute in the limits of integration, which is just going to be 2 pi minus 0, or 2 pi. So B equals mu naught I over 4 pi r times 2 pi. Obviously, the pi cancels, and one of the 2's cancels. And we're left with our magnetic field equals mu naught I over 2r. Well, that doesn't work, does it? So I will just draw the box, I guess. Got it? Mag field from a current loop. What an arc of current question will look like, but expect that an arc of current question is going to be, I mean, it's just not that complicated. Here's what an arc of current question will look like. They'll have a picture that's going to look ridiculously contrite, something like this. And it'll say current is going this way in this apparatus, or this bent wire. And something like, they'll say this is maybe 2 centimeters and this is 5 centimeters. And they'll say maybe the current is 2 amps, something like this. And they'll ask, what is the magnetic field here? Now, if you're as smart as I think you guys are, you realize that what I have here is about a quarter of a circle. Right? It's not one complete loop. But you'll note that this point is clearly being insinuated that it's at the center of whatever bit of arc I have there. You guys see that? And there's going to be 2 contributions to the magnetic field. There's a contribution to the magnetic field from this portion of the arc, which is closer to the magnetic field, and this portion is producing a bit of a magnetic field that is into the board. And then there's a portion of contributing to the magnetic field from this point of arc, or this piece of arc. But it's further away. But it's also going to be, in this case, out of the board. So I would expect that its contribution will be weaker. But now you need to ask yourself, what about this portion of the wire and, say, these portions of the wire? How are they contributing to the magnetic field? They're not. If you consider the cross product would produce a sign that is 0. Because if we consider ds from here, right, it's this direction based on the current, but r is this direction. So our ds cross r is equal to 0, because that's a sine of 180 degrees. You guys okay with that? And is it clear that it doesn't matter whether the current is going towards the center or away from the center? It's going towards the center. Suddenly our angle for phi is going to be 0 degrees. So the ds cross r is going to be 0 there as well. So this means 2 things for you guys. If a current is pointed at something, it creates no magnetic field in front of the current. Just like a charged particle coming at you will not create any magnetic field along the line or path on which it travels. It's just a cross product. Rules it out. So it only makes a magnetic field to the sides of itself. The side in front, the side in back, but not directly along and not directly behind. So just the little bits here, you're realizing now that a current passing through the wire is doing a lot more than just lighting up the light bulb. All of this is happening. It's creating electric fields and magnetic fields all at the same time. And when you start dealing with currents that aren't constant, you start dealing with magnetic fields and electric fields that also are not constant. That starts to create some crazy stuff. All right. And looking at where I am on the time, we don't have enough time to fully introduce and also do an example of Ampere's law. And I know you're saying, well, we just learned one law, Mr. Shelton. Why are you going to throw us another one? Because what we just did, really, really, really minor. Biot Savart is not likely to come up very much. You have seen what you need to know. And that is, Biot Savart is great at telling you the magnetic field at the center of a current loop. It is really, outside of that, not useful for much. But Ampere's law is. And Ampere's law is great. Because it's like Gauss's law, but a little simplified. So Ampere's law works like this. I'm going to write it out for you. This is one form of Ampere's law. We're going to see this law evolve as we learn more things this unit. We're also going to have to start adding stuff to Gauss's law, because Gauss's law is a little bit incomplete. So we're going to be doing Maxwell's adjustments to these laws over the next couple of weeks too. But this is known as Ampere's law. And it has really similar qualities to Gauss's law. if I put them both together, including the definition of flux, we had Q enclosed equals epsilon naught times the integral of E dot dA. But so they have a lot of similarities. On the left side is got that enclosed property, and the right side has some circled integral. Now, if we recall, Gauss's law was about the electric field. And in order to determine the electric field, we are calculating the total amount of flux in some closed surface that enclosed a group of charges. And that's how we did Gauss's law. Ampere's law is about calculating the magnetic field. But it's going to be a little bit different because we're dealing with the flow of current. So Ampere's law is about how much current you enclose. But we don't enclose it in a surface. Instead, we do what's called an Amperian loop. Instead of a Gaussian surface, an Amperian loop. So imagine I have some random wire in space, and that random wire has some current passing through it. If I wish to determine the magnetic field, or if I can measure the magnetic field and I wish to determine the current, then I will draw an imaginary Amperian loop. It has to be a completely closed loop that encloses a current. This tells me to add up all of the magnetic field along a single closed loop. If I add it up, this is what's called a line integral. So raise your hand if you've heard the word line integral before. This is a line integral. You're integrating across a closed path, a line. It will equal the amount of current enclosed.